that I'm recording this right now. Okay, so yep. So the second method here is by writing down the general formula for this. The only difference here, the only subtle thing here is to realize what's your very initial term. What does the very first n should start from? For example, in this case, you can see very easily that n start from equals to 1 and goes to infinity. Okay, and this is a second way to give us like a summary or sketch of what the sequence should be looking like. Okay, so this is called the general formula for the sequence. And you could have other different, so basically the sequence is nothing but a list of numbers. That's the most general kind of definition, a list of numbers. Okay, it could have some pattern or it could just be random. For example, another example would be example 2, could be the nth digit of the pi, or the first n digit of pi. For example, the sequence could be 3, 3.1, 3.14, 3.141, things like these, right? You can see the definition, the feeling of that, okay? So this is a sequence. And once we have that, once we know the definition of sequence, then the question is, why do we care about these things? I mean, why do we care about sequence, and what kind of interesting properties do we care, okay? For sequence, I mean, imagine this is something that we have been roughly talking about in terms of taking limit of a function, right? If you have a list of numbers, the most interesting would be that what's the tendency of the list, right? I mean, is the list of numbers going to somewhere? For example, in this case, you can see that for the second example here, this definitely goes to pi, right? So this list of number actually goes to pi. And for the other list here, for the one that list up above, 1/2n, the nth term of the sequence actually goes to 0, right? I mean, this is very obvious to intuitively speaking, right? I mean, there are other sequences which may not be very easy to understand from the very beginning. So that's actually our main job for this first two sections, is to understand how do we find the limit of sections, and what are the interesting properties we can use to help us to determine the limit of the sequence, okay? So for the first one, let me give you a couple of examples, and let me write down the very first sequence that might be very interesting, actually. Let's look at the sequence. I want to do a very, this is going to be actually a very technical one, but I think it's very important for later on study, is the following one. So this is actually, I begin with something which is not easy, actually. So this is actually the example I want to really talk about today. First is, what's the limit? Suppose the sequence is given by this, an, this is the general term for the nth term of your sequence, is given by n factorial over n to the nth power, okay? Do you guys understand the meaning of this n factorial term? So this means that, for example, let me give you something. So for example, 5 factorial means it's 5 times 4 times 3 times 2 times 1, which equals to, I guess, 120, okay? Similarly, you can have maybe 3 factorial equals to 3 times 2 times 1 equals to 6, okay? So the thing that you should notice is that by the definition, this term, you should have a general feeling about this, is that it grows really fast, okay? And this is the reason. This is the reason why this is actually a very interesting one, because the numerator grows really fast, like n factorial fast, and the denominator is like n to the nth power, right? I mean, this is also very fast. It's like 2 to the second power, 3 to the third power, 4 to the fourth power, things like these, okay? The question we are interested in is this list of number going somewhere? So let me write down the first few terms. For example, a1 equals to 1 factorial over 1 to the 1th power, which equals to 1, okay? And what about a2? a2 equals to 2 factorial to the 2 to the 2nd power, and that equals to 2 times 2 over 2 squared, which is 4, and this is 1/2. Okay. What about A3? The third term in this list is given by 3 factorial over 3 to the third power, which equals to 3 times 2 times 1 over 3 times 3 times 3 for 3 times, right? That's what the meaning of 3 to the third power means. So this actually gives you 2 over 9. And then let me keep writing this for the very last term, the fourth term, which is 4 factorial over 4 to the fourth power equals to 4 times 3 times 2 times 1 over 4 times 4 times 4 times 4. Let me mute all. Okay. And then this actually equals to, you can see from the picture here, this actually equals to 3 over 32, I guess, that if my computation is correct. Okay, so you have a feeling of that. You can see from the pattern here, it actually begins with 1 and gets 1 over 2 and gets to 2 over 9 and then becomes 3 over 32. You should have a sense of feeling after writing this many terms already that this is going to be very small, become smaller and smaller, right? So we have to, when something that is actually decreasing becomes smaller and smaller like these, what's a reasonable limit for the sequence? Should be 0, right? It's getting definitely decreasing each time and going to, seems to me that it's decreasing to 0. So let's see how can we justify this. And the reason why this is true, you can see by the way I'm writing this, you can already see that what is the AN's term? Okay, let's try to write out the term explicitly. AN is going to be to 1 times 2 times 3 dot 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 times n over n times n times n to n, right? This is n to the nth power in the denominator and n factorial in the numerator. Okay. So what can we do with this actually? I mean, does this actually give you some kind of hint why it's decreasing to 0 from this expression here? You guys see that? The reason why this actually is decreasing to 0 is because which one is larger, 2 or n, 3 or n, or dot 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 to n over m? Each of the term here is what? Is smaller equals to 1. Do you agree? So if that's the case, we can safely see that an is going to be smaller than 1 over n, because all these terms are smaller than equals to 1. Make sense? So if the an's term is actually smaller than 1 over n, what happens when n goes to infinity? This side actually goes to 0 as n goes to infinity, right? And because this is actually always positive, so it has to be something non-negative as a limit. So this gives you that the limit when n goes to infinity of an, this actually equals to 0. Okay. So this is actually the very first example I want to do, is to give you a sense on how do we determine if the sequence has a limit, and how do we determine the limit itself actually. And this is actually the first one, which is by very clever tricks and observations of the sequence itself. But in general, how do we do this in general? Like in general, we do this using, we can use all the techniques we have learned so far about limits of functions, because roughly speaking, what is a sequence? A sequence is nothing. So I mentioned that previously, like a sequence is a list of numbers. But the second interpretation of this is that a sequence should be interpreted as the following. Also, a sequence can be interpreted as a function. But this is not a function defined on real numbers. On the other side, this is a function defined only on integers. Okay, so basically you are defining a function on an, what's the meaning of an? An is nothing, you can think about this as a of n. That means give a number, an input, like an order. I'll tell you what's the number on this location in the list, right? So this is like a function. I mean, if you're a computer science major, you should understand this very easily. This is just a list, right? I mean, nothing fancy about that. And once we have that, given this understanding, suppose we understand this as a function, then to find the limit of function, we have various tools to do that. In particular, we have L'Hopital's rule to help us. Let me give you some examples and how does this help, actually. And there's something that's very subtle. I want you guys to actually, not very subtle, but very, you have to be careful about the way you write answers. Okay. So let me give you this one first. So how do we define the limit, determine the limit of n goes to infinity, for example, this kind, n squared over root n cubed plus 4n. How do we determine the limit of this sequence? By writing this, I mean, this is my an's term, okay? So if my sequence is given by this general formula for each n, and my question is, what's the limit as n goes to infinity for the sequence? Okay. Anyone who wants to give a try on this one?
Well, it's infinity over infinity, right?
Yeah, it's n goes to infinity. And so what's roughly the order of the denominator? It's like, by order, I mean, it's like n to the first power, n to the second power, n to the third power, or n to the maybe the 1.7th power or something like these. And can you determine what's the order of the denominator first? Which one actually dominates? I mean,
yeah, the highest one for the denominator, I guess, would be 3/2.
Yes, and you have a square root, and that gives, just like Brian said, it's actually 1/3, right? I mean, sorry, 3/2, right? So that means the order of the denominator is roughly like n to the 3/2. What's the order of the numerator? It's like n to the second power, right? And which one is larger? Actually, you can see there obviously this one is the larger one. So this gives you a heuristic that if the denominator behaves, when n is very large, behaves like n to the 3/2, whereas your numerator behaves like n squared, then obviously this one grows faster, right? So the intuition should be that if this one grows faster than these, then this goes to infinity, right? So the only thing remains is to justify our intuition, our heuristic. Why is this going to infinity? So what we can do is we can do the following. Since we are interested in either one of these, so we can divide by n squared or n to the 3/2. It depends on you, but let's do dividing the numerator and denominator both by this term and see what happens. If I divide the numerator and denominator at the same time by these, so the whole ratio will be remaining the same. So I get the following. So I get the following thing. So the following is, I get n to the 1/2 in the numerator, and I get square root 1 plus 4 over n squared in the denominator. Do you guys agree with my computation here? Sorry, let me. So I'm dividing both the numerator and the denominator at the same times by n to the 3/2, and I'm writing this term in the same fashion as this term here, okay, which is square root of n cubed, which is the same as 3/2, n to the 3/2. Now I'm merging this term into here so that you can see why this is becoming 1, because when you divide these two, this term got canceled out, and the leftover for this is going to be 4 over n squared. That's how you get these. And now in the numerator, you get n to the 1/2, right? I mean, this is nothing surprising when you divide these two things, okay? So when n goes to infinity, you can see that this term goes to 0, because when n is really large, this term just is nothing but 0. But this term actually goes to infinity, right? So the whole limit when n goes to infinity then is infinity over 1, which is infinity, right? So that's how you see, how do you determine a sequence, a limit of sequence of this fashion. I mean, you can see the flavor. It's very similar to the kind of thing we learned about polynomials. Suppose you have a polynomial of degree 2 in the numerator, you have a polynomial of degree 1.5 in the denominator, then you can determine the limit, right? I mean, you can basically, it's the order of the leading term that determines the limit, right? The coefficient of the leading terms, right? So that's how we determine this case. And you can do something similar. For example, you could have n to the 5.7 over n to the 11.3 plus n to the 3 plus whatever, blah, blah, blah. I mean, this is a very similar idea to the limit of a function where the function is given by ratios of polynomials and rational expressions of the same kind, okay? So be careful with this kind of questions. I mean, if on the next exam, anything would happen on sequence, I mean, it would be something like this: determine the limit of the sequence, and there are not many choices, okay? And then the next example is the following one. So the next example is actually given by, how do we determine the limit of this expression where n goes from 1 to infinity? So what's the limit of n goes to infinity of an, which is the limit of n goes to infinity of n squared e to the minus n, okay? And any suggestions? How should we attack this problem?
Maybe rewrite it as a rational function.
Yeah, that's the first move. Let's do that. So this is going to be n squared over e to the n, right? And then what? How do we determine the limit of this expression? I mean, you see the similarity of these. Suppose you replace n by x. This is something we have done already. This is a polynomial in the numerator, and you have an exponential function in the denominator, right? Except in this case, they are not really functions on the real numbers, but they are functions of the integer numbers, right? So how can we justify the use of Lebedev's rule? Because that's something we can quote, we can use actually for real functions, right? Really for authentic functions. So what we do is we change the variable first. This is something I want you guys to be careful. You don't apply Lebedev's rule directly to this expression. That will be totally wrong, because can you differentiate integer numbers, right? There's no way you can differentiate the integer numbers. So you cannot use L rule here, as it is not even a continuous function even, right? So because this is not really, even it's not a continuous function, so how can you apply Lebedev's rule which involves differentiation? There's no way you can do this. So that's why you first switch the variable's name to x. And the reason why these two limits are the same is the following. Suppose you have a bunch of dots, 1, 2, 3, 4, things like these, right? Suppose you have a bunch of dots here. If the dots is actually going somewhere, then if you can connect the dots by some reasonable function. Did you see that? You should be expecting that the limits of the sequence of dots be the same as the limit of the function, right? Which is very reasonable, intuitively speaking. And that's the reason why these two are actually the same, okay? So then we can code the Lebesgue rule to here, and we get limit, sorry, this is x. X goes to infinity of 2x over e to the x, which again equals to limit x goes to infinity 2 over e to the x, which goes to 0. I'm applying Lebesgue rule twice to get to 0. Okay. So this is how you solve a problem like this when you use Lebesgue rule. So let me remind you guys again that on the exam, if you directly apply Lebesgue rule directly to this step, that'll be totally wrong. And you'll be missing a lot of points for doing something like this, even though you're doing almost the right thing, but conceptually that's totally wrong, and this is unacceptable to math people. Actually, you should be very clear about the concepts. So that's why you have to switch the variable's name to x and then apply Lebesgue rule afterwards. Okay, so that's the kind of question I want to remind you guys when you have a question like this on the exam or website. Actually, okay. So that's the two examples I want to see, actually. And the one last example, which is a small test of your knowledge of arctangent. So let me skip the very last example on limit of sequence before we move on to something else. The last one is given by this example. What's the limit of when n goes to infinity of an, which equals to, let me give a bracket, which equals to arctangent log n. Okay, so my sequence is given by arctangent log n, and my question is, what's the limit of the sequence here? Okay, let me write it more appropriately. So this is limit n goes to infinity and of arctangent log n that we are interested in. Okay, so how do we know that? How do we know the limit for this one?
Like pi over 2 or something?
Yep, thanks. That's quick. So this one actually goes to infinity, as you can see. And what's the value of arctangent at infinity is pi over 2, and nothing more than that. Okay, so the reason why I give you this example is this kind of evaluation appears a lot later on in the semester, so you better know it now before you know, to save you some trouble when you get stuck on the exam. Okay. So for the next, so this is everything I want to see about the sequence and how do you take limit of that. And for the remaining time, I'll be sending out, give you a screenshot of the worksheet we are doing today, and you can work on that and make sure you turn it in once you finish. And also you can take a picture of the screen and so that you can finish on time. Okay, it's only 2 problems, and we won't be using the worksheet from the .checkweek this time actually. So let me give you share the screen. Okay, so so let me see, how do I do that? Okay, quiz 8 over here. Oh, let me do it again. Actually, not this one. New share. Okay, it should be the Acrobat. Let me find the right worksheet I want you guys to do. Oh, actually, I think that's the right one I want. Okay, so let me do this. Just give me 1 second. Can you guys all see what I have here on the screen?
Yes.
Okay, is it clear? That's on the screen that you can see that? Okay, perfect. So there are only 2 questions. The first one is about the Taylor polynomial, and the second one is actually for determining the limit of sequence. Okay, I want you guys to, for the remaining like 30 minutes, try to work on these two things and finish and turning something afterwards. Just taking a screenshot of a picture and upload as a PDF version to Canvas. Okay, and that will be counted as your grade for this worksheet.
Where will we upload it to? There doesn't look
The
like
Canvas.
an assignment. But okay.
Yep. Under the name of worksheet 9.1 to 9.2. If you have any questions, you can always ask me. I'll be around actually. So
Is it the one that says it's due? It's 9.1, 9.2 / 9.3. It's just due this, I guess, April 20th.
oh, actually, yeah, even though it's due, but I'm changing the question. So this is only 2 questions. You can work on these and see. Maybe I can make it due maybe later today, but at least try to work on these so that since I'm around, if you have any question, you can always ask me about these actually.
Thank you.
Yep. Oh, sorry, I shouldn't be moving that. Okay. Have you guys all take a picture of this screen here? If yes, type yes to me so that I can switch a screen to something else. Okay. So everyone has take a picture. Okay. So I'm going to stop screen in about in 3 minutes. Okay. Okay, perfect. Okay. Do you guys know how to actually upload this? I mean, or how to send the file to you guys within Zoom? Or is there a feature like this for me to send files to you guys actually? That should be, yeah. Let's see. Okay. Oh, leave it as a factorial. Thanks for saying that. So, but I guess in this case, no, actually simplify it because this is only up to degree 5. So there's only 3 terms that's involved. So the best way to do this actually is, yeah, simplify it.
So I have a question about the second problem.
Yep.
So it's, I guess the index starts at n equals 2.
Yes.
So would the first term be, would the notation be a sub 2?
Yes.
Or would it still be a sub naught or a sub 1 and then just plug
So
your
that
2
means
in
there's
for n?
no A1 in this sequence.
Okay, there's no a naught and there's no a1. It's just a2 is the first term.
Yes. So
Thank
this
you.
is one of the reasons why I give you this question is that the leading term is just totally determined by the very initial n. It's not necessarily going to be n equals to 0, n equals to 1. It could be anything, actually.
Thank you.
Yep. Okay, how many of you actually got number 1? I couldn't see you raising your hand, so I have to ask. I mean, anyone who hasn't gotten number 1? Or anyone who has got number 1, I guess. Do you guys want me to divide you into small groups for you guys to talk to each other? Or do you want to do that? So I just break you guys into 2 different rooms, just like the groups. You can talk to each other within the group. And I think that'll be helpful if you want to discuss with each other. Yes. Yeah. You mean
Bo, can you go over how you would solve that, the highest degree of P13 and 24?
so? You can already see from the pattern that the terms appearing in the power series of sine function are all odd, right? The first term being x, the next term being x cubed, the third term being x to the fifth power with appropriate coefficients. So is 13 an even or odd number? And then what about 24? And that's actually, yeah.
So the highest polynomial, the highest degree of the Taylor polynomial of sine for 20 P24 would be 23,
Yes.
and
yes.
then 13 would be 13.
Exactly.
Okay.
Yes.
And then did you get my message about the second one?
Yep. Let me see. Oh yeah. Yep. 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 I got you and Justin. Both
Thank
of
you.
you are right, so don't worry. And where is the? Let me see. But have you write out the first three terms in the sequence?
Yeah.
You guys are supposed to write out the first few terms of the sequence.
Yeah.
And yep, okay. Let me see.
Oh wait, of the sequence, not of the Taylor polynomial.
there's no Taylor polynomial involved for the
Right,
second question.
right,
It's just
right,
a
right,
sequence,
right.
and I'm talking about the limit
Yeah.
of the sequence.
Right.
Okay, any questions from anyone? Once you finish, you can upload the answer and you can leave the room.
Bo.
Yep.
So I'm looking at the assignment that's on Canvas,
Mm-hmm.
and there's two worksheets posted here, but we're not
Yes.
supposed to work with these. We're just supposed to do the one you gave us.
Yes.
So ignore these worksheets.
Yep.
Okay.
As a reward for anyone showing up today.
Yeah. Beautiful.
Because I mean, the worksheets Dr. Chadwick uploaded is kind of off the point. I would say that's
It
not
looks
going to
pretty
be.
hairy.
Yeah. Trust me. I mean, it's not going to help too much.
Good.
Yep.
Okay.
Yep.
Great.
Yep.
Okay. So we just are supposed
Understand
to
the
upload this.
basics are more important right now, actually.
Beautiful.
Yeah,
Thank you.
especially after the previous exams through, you can have a feeling that the exam will be harder in the sense that you are given a textbook at home, but on the other side, it will be easy in the sense that there won't be like really technical problems. It will be something that once you understood, you should be able to do kind of questions. So that's why
Right.
we need to focus on the basics rather than going to work on some fancy hard problems.
Right.
Yeah.
Right.
Before that. Yeah. So that's my
Got it.
point. And also the two. And also he told me basically that I can choose either one to be the assignment. So I said no. Actually, I'm going to do mine. So yeah.
Perfect.
Yep.
Thank you.
Yep. Okay. So once you finish, you should be able to upload your work onto Canvas and that's it.
Okay. Thanks, Bo. Have a
Yep.
good day. And same thing on Thursday then, yeah?
Yep. Same thing on Thursday. There will be another worksheet. Yep.
Thank you so much. All right, have a good one.
Bye.
Bo.
Yep.
Hey, so it's just me. And now,
Yep.
I wanted to.
Let me
Is
stop
that- so I-
recording first, so I don't want you to show
Oh,
up on the
okay,
video.
yeah.
So let me stop.